Okay, again, this is a continuation of our discussion about determining whether the argument is valid or invalid. This time, we're going to use a different method. From our first two videos, we talk about determining the argument using to be valid or not valid using the truth table. The different method that I'm talking about is the method that uses the standard forms, or we call that the valid argument forms. Following are the list of standard forms. We have actually 6 standard forms now. How do we use these forms to determine whether the argument is valid or not valid? After writing the argument in symbolic form, you only need to compare it with the valid argument forms. If there is one valid argument form that is of similar form to your argument, then without using the truth table, you can already say that your argument is valid. Okay? And these are the argument forms which are considered already to be valid. These were proven, of course, by using the truth table. Okay, the first one is called as the modus ponens, or the direct reasoning. It is of the form P implies Q for your first premise and P for your second premise. Therefore, the conclusion is Q. So you will see that this is called as direct reasoning because if the statement is if P then Q, then P is true, that means that Q is also true. So therefore, the conclusion, therefore, Q is valid. Okay. For modus tollens, or you call that contrapositive reasoning, you have if P then Q, then the second premise is negation of Q, the conclusion is negation of P. You call this contrapositive modus tollens or contrapositive because remember, if you have P implies Q, the contrapositive of that is negation of Q implies negation of P, which is of the same truth value with P implies Q. So using contrapositive, when negation of Q is true, that means that the negation of P is also true. Then the third one is called as generalization. It says that if you only have one premise, no, which is P, then you can say you can actually conclude that P or Q is true when P is true. In other words, what we're saying here is as long as P is true, it doesn't matter whether your Q is true or false, as long as the connective you're using between P and Q is or. Okay, same is true with this, of course. No, as long as Q is true, P or Q is always true. Okay, so you call this generalization. Like for example, if we say that I am a mathematician, then if you conclude that I am a mathematician or an engineer, then that's a valid conclusion. Okay. Number 4, you call this specialization. It says P and Q. Okay, this is you only have one premise. Okay, P and Q. Now you can either conclude P or Q, because when you say P and Q, take note that the premise is always true. So if it is always true, there is only one case where P and Q is true. That is when P is true and Q is true. So therefore, if you conclude P, that's a valid conclusion. If you conclude Q, that's also a valid conclusion because P and Q are true. Then we have elimination. You have P or Q, okay, to be true, but negation of Q is true, so that means that Q here is false. So that leaves for you to conclude that P is true. That's why the correct conclusion is P. Also here, if P or Q is true being a premise, and negation of P is true, because that's a premise, so that means that your P is false. So that leaves only one possible truth value for Q, which is true. That's why the correct conclusion is true. And then you have transitivity. P implies Q. Q implies R. Therefore, P implies R. The transitivity is a familiar property, right, from algebra. If you remember, you have transitive property of equality. If A is equal to B, B is equal to C, then therefore A is equal to C. Same is true with this. If P implies Q, this Q implies R, therefore P implies R. You call this a chain of conditional statements, no? Then when you have chain of conditional statements, then the hypothesis of the first conditional implies the conclusion of the last conditional statement. Okay. We also have a form which is called as standard form for invalid arguments, and there are two of them. We call this the fallacy of the converse. Take note that the converse of a statement is not of the same truth value with the conditional statement. That's why if you have P implies Q and then Q is true, it is not correct to conclude P. Because as you can see, if your P implies Q is true and your Q is true, this is true, okay, then your P is either true or false. That's why it is not correct to conclude P. So there is no correct conclusion that you can actually make from here, no? Fallacy of the converse. The converse is not true when your P implies Q is true. We also have what we call fallacy of the inverse. P implies Q, and the negation of P is true. It is not correct to conclude negation of Q, because the inverse again is not of the same truth value with P implies Q. Okay, so P implies Q, and then you have negation of P. The negation of Q as conclusion is not correct. Okay, let's illustrate this using some examples. Let's try this one, and we will refer to the list to determine whether this is valid or not valid. Okay, let's start with our first example. First, convert this into symbolic form, and then after that, check if there is a valid argument form that is similar to your argument. Okay. So if my glasses are on the kitchen table, we have K here. Then I saw them at breakfast, so K implies S. I did not see my glasses at breakfast, so that means this is negation of S. Then we have, for our conclusion, therefore, my glasses are not on the kitchen table, so this is negation of K. So which form is satisfied by this? You have K implies S, the negation of S, therefore negation of K. That's actually similar to what we call the contrapositive, right? Contrapositive. You can check here the form. P implies Q. It's similar, no? P implies Q, negation of Q, the negation of P. So because that's similar to the form for contrapositive, we can say that this is a valid argument. Okay. Second, this is already in symbolic form, so you only need to identify the argument form that is similar to this one. Okay, M implies negation of N, then you have M, therefore negation of N. What is that? If we check our list, that's actually similar to this particular form, right? P, this stands for your P, then it stands for your Q, then you have P, then the conclusion is your Q, right? You call this the modus ponens, or direct reasoning. So we say that this is valid because there is a similar form, okay, from our list of valid argument forms. Third, H or J, negation of H, therefore J. Okay, is this valid or not valid? Okay, do we have a form that is similar to that? We actually have a form that is similar to that. We call that the elimination, right? You have P or Q, elimination, the second form for elimination. This one, okay? P or Q, okay, this is your P, this is your Q. The negation of P, therefore Q, right? So it is similar to that, that's why this is valid. Third, fourth, okay, again we convert this into symbolic form. You have G implies S. If the stock market will fall, is S, implies I'm not investing in the stock market, so that's negation of I. Therefore, if the price of gold rises, that's G, implies I'm not investing in the stock market, so negation of I. Okay, as you can see, this is similar to what we call transitivity, right? G implies S, S implies negation of I, therefore G implies negation of I. So this is valid by transitivity. And last example for this video, we have Abraham Raymond is a mathematician, that's M, okay, and an engineer, so and E. Okay, therefore we only have one premise, no? Therefore Abraham Raymond is an engineer. Okay, what valid argument form is this? This is actually what we call a spatialization. That's a spatialization. P and Q, therefore P, or P and Q, therefore Q, right? So M and E, therefore E. So this is a valid argument.